Let's start section 6.1. Start in chapter 6. We're going to talk rational exponents now. So there's a lot going on in this chapter because now we're talking about roots, but we're also squaring to get back to x. The way the book starts out is by explaining that we have square root of x. That's the positive square root of x. So when we take square root of x and square it, that's how we get back to x. The big key is going to be thinking about multiplying that radical expression by however many you have. If it's a square root, that means you're dealing with twos. So if you square it, you get back to the beginning. Then we can negate it and carry out the work as always, but have a negative in front, and we just ended up negating the answer. So that's how the book starts out. I said, let's think about it this way. Think if we have a square root of x, if we square it, we get to x. Well, if we have a cubed root of x, we cube it to get back to x. Fourth root of x, we go to the fourth to get back to x. Nth root, go to the n to get back to x. So as long as this number matches up here, it cancels the radical out. So square root, the square root squared gets you back to x. Cube root cubed gets you back to x. Any nth root to the nth power gets us back to x. Now, and terminology wise, I'm going to avoid it because I don't want people getting confused with radical, radicand, and index. But this is what it means. This is the index. That's the amount that you're taking. And here's your radicand. So radical sign is just your symbol, your square root, cube root symbol. You've all thought of it as square root up to now, but now we're dealing with cubes and any number actually. So for examples 2 through 6, they just start giving us some examples. Now, with cubed roots, this is where we start switching gears a little in our thought process and what we're looking for. For cubed roots, they're really going to work with 8 and 27. Those are the two biggies to watch for when you're looking at cubed roots and trying to pull things out. If you see 8, you know it's a cubed, you know it's 2 cubed. If you see 27, that's 3 cubed. So 27 is cube root 3, 8 is cube root 2. So when we have the cube root of negative 8, when we have an odd index, when that's odd, we can have a negative. So you can have a negative under this. You think of it as a square root symbol. It's the radical sign, but under that radical you can have a negative number as long as it's an odd index that you're looking for, because what this means is what number times itself 3 times equals 8. What number times itself 3 times equals 8? That's 2. Well, we're just putting a negative in there. If we multiply a negative 2 by itself 3 times, we have a negative times a negative is a positive, times that third negative gives us a negative. So the cubed root of negative 8 is negative 2. Now, I'm going to erase all this. You've already got it. If they give you an even index, with an even index, we can't have a negative. That's where we get back to the idea of square root. When you start thinking square root, you can't have a negative. So they toss this as an example. There is no answer. Square root of negative 4. Well, we know that if we take a negative times a negative, it's always a positive. So whenever we have an even index, we cannot have a negative number. You'll always have a positive. So you can't, that's not a real number. Now they can say, they can go this route. This is another one that sometimes throws students off. when they throw a negative out front, there is a value. There's a value to square root of 25. Just like if someone writes 5 squared, they mean 25. Or it represents 25. It's the same. 5 squared is 25. 5 squared is a fancy way to write 25. Same here, square root of 25, fancy way to write 5. That's all it is. So we know that value, square root of 25 is 5. Well, when we have a negative symbol out front, that just means negative whatever follows it. Well, what follows it is the square root of 25. So, well, I'll stick with this just to make sense of it. Square root of 25, that is 5. I'm just saying it's negative whatever that is. We're going to negate the answer. So even if it's an even index, we can have a negative if that negative symbol doesn't really have anything to do with the radical sign, which it doesn't. It's out front. And then, again, fifth root, they give us fifth root of negative 32. It's an odd index, so we can have a negative. So there is a value to that. 2 times itself 5 times is 32. And because that's an odd index, I can have a negative answer. And then they go with fourth root of negative 81. And the key is the negative is here. It's not a real number because I have an even index. So with my even index, I would multiply that negative. That 4 means this. I would have negative times a negative times a negative times a negative. I'd end up with a positive. So that's not a real number. Now, they're going to shift gears a little. They're just setting the stage to help us understand what the radical sign does, what all those numbers represent, and how we work them. Now they switch gears to variables under the radical. Examples 7 through 9 now, they give us, and I'll break the first one down a lot, the second one down a little, and then we'll just do the third one, because I want you thinking shortcuts whenever possible. B to the 6th. So what they're saying now, the way we look at these, is we think, well, it's the same thing as saying square root of 25 times square root of a to the 4th times square root of b to the 6th. When you're thinking this, you already know part of this answer is 5. When they give you something like this, think of it as square root. I'm going to write my 2 for an index. I want pairs. So I want to see how many pairs do I have, what do I have pairs of? Well, a to the 4th I could break down as a squared times a squared. The key is make this index match up with your exponent underneath. There's many different ways to think about these, but I try to explain it best I can. Make the index match with the exponent and then see how many of those you have. If something's left over, you leave it inside. So a squared, and I index a 2. I have 2 of them. A squared times a squared is a to the 4th. Well, every time I have an a squared, I'm pulling 1 out. 2 divided by 2 is 1. So for the squared root, I'm going to use my 2 just so that we can see what's going on. We go back to that idea that I wrote at the beginning with when the index matches up with the exponent, we go back to just the regular radicand, or just the regular value, I should say. So we're looking for numbers that match up. Here, I still have a squared root. But I have b to the 6th. So there are different ways to view this, but if we go this route, it helps you see what we're really doing. B to the 6th. I can get 2's out of that. I know I'm dealing with a 2, so I need 2's for my exponent. B to the 6th, I can break it down as b squared times b squared times b squared. Because again, our rule says 2 plus 2 is 4, plus 2 is 6, there's b to the 6th. So then I just count how many I have. So right now, I know my Square root of 25 is 5. Square root of a to the 4th, well, I have 1, 2 of these. So I bring one out. Maybe I can break that down one further even for this one. We won't do this much work after this. Pull one out, pull another one out, a times a. Here, pull one out, b. Pull another one out, b. Pull another one out, b. I end up with 5a squared, b to the third, b cubed. The simpler way to look at it is to say, how do I make the index equal the exponent? 2 times 2 is 4. I got 2 of them. How do I make the index equal the exponent? 2 times 3 is 6. So I bring out b to the cubed, or b cubed, sorry. Alright, let's do another one. We won't break it down quite that much. Hopefully my voice holds out. I want to do 3 videos this morning to get them posted. Alright, we'll go with cube root of x to the 6th, y to the 12th. Now, we can think this route again if we want. Cubed root, I need to bring out 3's. Well, I have 2 of them in 6. X cubed times x cubed, 3 plus 3 is 6. And then I have y cubed I have 4 of those. If I bring out a y cubed, because I want my index to match my exponent, that way I know I'm pulling one out at a time. Well, I have 4 of these. 3 times 4 is 12. I want you thinking that route. So I pull one out, and I get x times x. Pull one of these out, pull another one out, pull another one out, pull another one out. What I have is x squared y to the 4th. So from here on out, what I want you to think is divide, or what makes this. 6 divided by 3 is 2, x squared. 12 divided by 3 is y to the 4th. You're just saying divide the exponent by the index. Or think, well, how do I make the index equal the exponent? How do I make this index equal the exponent? I would multiply it by 2 to get 6. I would multiply it by 4 to get 12. Or you think the other route, 6 divided by 3. Exponent divided by index, 2, x squared. 12 divided by 3, y to the 4th. That's the simpler way to think about these. So when we go this route, my 4th root of 81 is 3. My cubed root of 27 was 3. I multiply that by 3 and I get 81. So 4th root of 81 is 3. They don't give us those bigger numbers too often. Again, typically we're dealing with 8 and 27 when they're talking cubes. And then I take my, it's all going to fit on the screen. I take my 4th root of R8, and I can say 8 divided by 4 is 2. And then I take my 4th root of S20. 20 divided by 4 is 5. So my answer to this is 3r squared s to the 5th. You don't have to do any work with these. You can look. There's not necessarily any work to be done as far as steps. You can just take and figure out what times what. 4 times equals 81. You're not going to have that too often. You know it's 3. But then with our exponents, with our variables and exponents, all we do is divide. 8 divided by 4 is 2. 20 divided by 4 is 5. And that's our answer. So what we're going to end up doing is quitting here for part 1 video, and then we're going to go to rational numbers as exponents and do examples, I don't know, 10 through 14, and then they give us 25 examples, so we're going to pick and choose which ones we do. So I'll see you in a couple minutes.